And what's like, so a big company like GE, as I mean, they were on kind of the forefront of big investment in the technology. How does that, uh, how does the idea of a new technology kind of make its way up the validation uh, ladder in a big company like that? Because a lot of companies, especially, I mean, you even say today in manufacturing, right? That, hey, we've heard about additive. We see some of the case studies, it makes sense, but it's the risk is still too high for companies to make a big bet like that. Even whether it's GE making billion-dollar bets, or if it's a small kind of manufacturer where 750 $1 million for a machine is tough to swallow with some of that risk. So how did GE create a culture where it was like kind of diving into this new technology? Like, how did that kind of manifest itself? Because it seems kind of unique in terms of a lot of the other kind of big companies and just generally how manufacturing works. It's not every day that they make like these big step changes, it seemed.
Well, look, it's a special place. I mean, so they have been watching the technology almost since the outset. And actually, one of my slides that I always used to love to show was from colleagues of mine at GE Global Research, Bill Carter and a few others. They actually wrote a SFF proceedings paper in the early 90s where they were one of the first to do metal sintering, right? Because the original invention at University of Texas was polymer powder bed laser. And then it was really quickly, it was like people that were doing metallurgy were like, oh, hey, we can use metal powder. So it's like, so I wrote a little review paper a few years ago talking about this. It was like, okay, in the early 90s, GE Global Research, they took pure iron powder, they sintered it to like 30% density. And I love the last line of that paper. They said, I'm trying to remember what year it was. I think it was like 93. And they said, we demonstrated feasibility. This will eventually become a standard approach, right? And they were right. So a company like GE, they had been watching it for years and years in their research enterprise. And then it's like, okay, when do you have the big enough application pull matched with the right level of maturity, the technology to pull it through and invest in something big? And so for them, that was the LEAP engine. So LEAP engine, single aisle, 737, Airbus A320. So these are the like Columbus to Orlando, Disney World shuttle back and forth 13, 14 times a day, 1 2-hour flight. So the issue with those flights is the takeoff is when you really stress the engine. That's when you have the highest power, highest temperature, highest stress on the engine. In order to make the engines more efficient, you have to run them at a higher temperature, right? So you have this combination of the single aisle jet, so you have 13, 14, maybe even more takeoffs per day with the higher temperature for higher efficiency. That really stresses the combustor section and the high pressure turbine of the engine. So they had this drive this would be like late 2000s is when they started developing this stuff for more efficient fuel injectors, right? So this became the fuel nozzle program because you really couldn't make it any other way. There's a really complex internal geometry. The previous technology was a really complex brazing operation that actually you could almost argue is additive, where you take these like layers of metal foil and you braze them together in these complex shapes. But they couldn't get the heating, so they use the fuel, so the fuel gets warmed up, goes through this heat exchanger, and then gets atomized, and that's actually the flame that drives the engine. But they couldn't get enough cooling or efficient enough cooling to have the nozzles survive the duty cycle they wanted to do all these 13, 14, 15 takeoffs every day. So then it was like, okay, additive had been there on the shelf, and then it was like, okay, here's an application. We need this for the performance of this program. And then it sort of pulled through and then was sort of this like co-development, and that led to this whole growth. And then once you had an application where it pulled it through, there was the success story. Then you had all these knock-on applications. It's like, well, people don't necessarily realize. So, and this isn't just for GE, but all these gas turbines are applicable in power plants. There's a lot of oil and gas applications and just sort of like general industrial processing where you have compressors, things like that. There's a lot of ships that actually are driven by aeroderivative gas turbine engines. So that sort of technology for laser powder bed fusion being applicable to brazed fuel injectors, that was much bigger than just one program, right? And brazing is a really challenging technology. So the benchmark, so it was just like, okay, additive had been on the shelf. And look, all these other OEMs in the space have been looking at it. It's like, okay, just sort of slowly marching. And then finally you have this killer app. And then you have a big acquisition in the space like Morris Technologies. And then it's like the floodgates open, right? And then you get like America Makes is founded at about the same time, big corporate investment. And look, we're seeing the dividends from that now, right? Like all these other partners that we now have in my role at OSU. Well, we'll get to that. Okay, I'll take a break.
Yeah.